Good morning. So let us continue. So we have seen that in an enclosure, when there is a fully developed fire, we can see that there is a steady state condition, like the fully developed fire is a steady fire, and based upon the opening available in the enclosure, we can see that hot gases go away in the top portion and cold air enters in the bottom portion, and there is a formation of a neutral plane which is at a particular height from the ground or the floor. Okay, so we have also seen the mass flow rates of the incoming air and outgoing air. First, we found the velocities of the gas leaving as a function of z. So these gases leave above the neutral plane. So neutral plane z is 0, that is fixed as origin. So z equal to 0 at the neutral plane, and velocity basically varies with z for the gases above the neutral plane, and similarly for the air which is coming in, the velocity which is coming in, magnitude of velocity is given here, and we can see that this is due to the pressure difference. We already seen that. So based on these velocities, we have calculated the mass flow rate of the gases in and out of the enclosure. For example, the mass going out can be written as some coefficient of discharge CD into integral of the mass flux into area, that is rho g Vg into dA. Similarly, by substituting the values of the Vg expression, we get this expression for the mass going out, which is CD. W is the width, height of the opening vent is h0 and the width is W. Rho g is the density of the gases, which we have assumed to be uniformly distributed over the enclosure, rho g, and temperature of the enclosure is Tg. So now this is the pressure drop basically, and we can see that Zu is the, so if this is a neutral plane, this height above the neutral plane is Zu. So we can see the mass flow rate out of this. Similarly, we have derived expression for the mass flow rate of the air coming into the compartment, where this is neutral plane and this is the floor, and this distance is ZL. Okay. Now, for this I need to calculate the location of the neutral plane. So this is the floor and this is the ceiling, and this is the neutral plane. So this HN, and this height is H0, the opening vent. So we can see that this is also ZL and this is ZU. So now we can see that H0 equal to ZU plus ZL. So combining this equation plus, for steady state condition, the mass flow rate of the air coming in will be equal to the mass flow rate of the gases going out. Steady fire is steady. Okay, so the amount of smoke or the hot gases which are produced goes out steadily. Similarly, air comes in for the combustion. Okay, so at that condition, the mass flow rate coming in equal to mass flow rate going out. So when you equate this, I get an expression for combining this Zu and Zl like this, and we have one more expression, H0 equal to Zu plus Zl. So from this I can find the value of Zl. Once I know the value of Zl, Zu can be found and I can get the mass flow rates. So here typically the mass flow rate can be written as 2 by 3 CD area of the vent opening AO root of H0 into root 2G rho A. Now these are all, see, for example, this will be experimentally determined. A0 is known, H0 is known, rho A is also known. CD can be determined by experimenting, maybe 0.7, 0.8 or some variation will be there based upon the conditions. Now this under square root, there is a factor which is called density factor. Now density factor can be written in terms of temperature. Here delta rho can be written as delta T, and this, for evaluating this, we have used the ideal gas equation of state P equal to rho RT. Pressure is assumed to be constant at atmospheric pressure, 1 atmosphere. So from that I can say that the value of rho can be 353 by T approximately. So if I plot the density factor versus the gas temperature to the air temperature ratio, I get a curve like this, and maximum is found somewhere around 2.72 here, and after that the density factor doesn't vary much. So from the experiments, people have told that the value of density factor can be taken as 0.214, and say if you use a CT value of 0.7 and ambient density of 1.2, then we can write the mass flow rate of the air coming in, which is also the mass rate of the gases going out, as 0.5 A naught into root H naught, okay, for steady fully developed fires. So this we have seen. So for the regime 1 fire, we can see that the mass flow rate is a function of vent height and vent area. Okay. So fully developed condition occurs only after the flashover, that is, for steady post flashover fires I can use this expression. So we have seen this. Further we have seen stratified smoke layer forms in a developing fire. Fire is developed, so smoke layer stratifies and descends down, and this is the, again you can see that there is a height of the opening and area of the opening A naught, and here what happens is, in the developing stage, the smoke tries to descend to a particular height, which is measured as HS from the bottom of the opening. HS from the bottom of the, so HS denotes the height to which the smoke has descended down, and this is measured from the bottom of the vent. So here vent height is H naught, bottom of the vent is here. At this stage what happens, the smoke partially leaves from the compartment to some part of H naught, and the air also comes in this particular within the smoke layer. So air entrainment occurs at two different levels. One, in the smoke layer M dot A1, within the smoke layer air entrainment occurs, and below the smoke layer also air entrainment occurs. Okay, now we can do the same analysis. If we take the scenario within the smoke layer, this is scenario within the smoke layer, we can see that there is a formation of a neutral plane which is at a height of Hn measured from the bottom of the vent. Now below this neutral plane within the smoke layer, I get the primary air entraining into the smoke, and within the smoke layer above the neutral plane the gases go out. So in this stage, for a given, this is actually not a steady fire, a developing stage. So at a given time instant, we can say that there is a location for neutral plane. So based upon that, there is a flow rate of gas out and air coming in within the smoke layer. Similarly, I can also determine the amount of air coming in below the smoke layer. But the correlations are not very easy because of the fact that there are variables involved like Hn, Hs, etc., which are going to be, as a function of time, it will vary for the growing developing fire. So some analysis are the factors which are going to affect, we can determine, which are like say rockets expressions for the mass flow rate going out can be given like this. Here you can see that primarily this factor A naught into root of under root H naught is appearing. Similarly, some density ratio like thing is given here, plus you can see that that is a factor which involves Hn and H naught. Okay. Now for the mass going out, we have to integrate between Hn and H naught, that upper portion of the neutral plane in the smoke layer. Similarly, the mass of air which is coming in basically is due to the mass of the air coming in within the smoke layer below the neutral plane, and the mass of the air which is coming in below the smoke layer itself. So, that expression is given here. You can see that this cannot be solved easily, because see, for the developed fire, for getting the value of Hn, we had some theoretical basis, but in this case a numerical approach is required to determine this. Now, we go for McCaffrey, Quentry and Harkler-Rode correlation, which is called MQH correlation. Okay, this correlation is formulated by considering energy balance first, where the convective heat release rate was written as the mass flow rate of air plus mass flow rate of fuel into Cp into the gas, hot gas temperature, which is considered to be well mixed, and the ambient air temperature Ta, plus there is a overall or global heat transfer coefficient, and Hk into At. At is nothing but the total internal surface area into delta T. Okay. Apart from the heat carried by the hot gases, so mass flow rate of the hot gases will be equal to mass flow rate of air plus mass flow rate of fuel. So, now apart from the convection due to the flow of the hot gases, there is some overall heat transfer coefficient or global heat transfer coefficient, and internal area multiplied by delta T is also considered. Here Hk is not basically a constant, and this has been subject of research in several experimental studies involving compartment fire. But now, to simplify, Hk is taken as constant, and also noting that mass flow rate of air is much larger than the mass flow rate of the fuel, we can neglect m dot f. Once I do that, I get an expression for delta T, which is Tg minus Ta divided by Ta, as Q dot C divided by m dot A Cp plus Hk At into Ta, which can be written in this way: Q dot C by m dot A Cp Ta divided by 1 plus Hk At by m dot A Cp. Now, mass flow rate of air, we know that it is proportional to density of air, atmospheric air, into area of opening of the vent and the velocity which is induced. So, that can be approximated as under root g into h naught. Okay. So, something like a buoyancy driven velocity. So, using this, the ratio of delta T by Ta can be expressed as a function of two non-dimensional numbers. One is Q dot C divided by rho A naught under root G H naught Cp Ta. Second one is Hk At divided by rho A naught under root G H naught into Cp. These are the two non-dimensional numbers designated as x1 and x2. So, delta T by Ta for correlation can be fixed as the constant times x1 power n, x2 power m. That is it. So, now you can see that the convective heat transfer rate can be measured, or it can be written as a function of the overall heat release rate. Then there is some methodology to estimate Hk. At is known, all other factors are basically known. So, Cp value can be assumed to be some average Cp of say air and so on. So, now once I know this, then I can fix this correlation. Here more than 100 experimental fires have been considered. Okay, now different types of fuels like gas, wood crisps, plastic crisps, liquid fuels, etc. have been considered. So, now that means different Q dot values and QC values are considered. Similarly, size of enclosures starting from conventional room fires to 1/8 size with varying construction materials like say wood, steel, etc., where see wood and steel have a wide range of thermal properties. So different properties materials are considered. So this was done by McAfee et al. In 1981. So once this experimental data were used and curve fit was done. Specifically, the first non-dimensional number is Zukowski number. We have already seen this. Q dot C divided by the enthalpy flow rate, rho A naught, velocity. See here in the original definition, instead of A naught we had D square. So G H naught was replaced by D. Now instead of that we are using A naught itself, that is H naught into W, and for the velocity the height actually induces the velocity. So under root G H naught is used here. So this is Zukowski number. That is known to me. Okay, the second non-dimensional number is something which actually relates the, see for example, if you multiply the numerator and denominator by delta T, it is like the convective flow heat flow rate in both the cases, correct? So this is another non-dimensional number. So now we can put some values here so that all the known variables can be converted into numbers. So G 9.81, air density 1.2. Similarly, ambient temperature, some standard temperature, so 20 degrees is taken here. Cp, some value 1.05 is taken. So when you incorporate all of this, I get delta T by TA equal to 6.85 Q dot C square by HK AT A naught into root of H naught whole power 1/3. Okay, here Q dot C should be in kilowatts. HK is the overall or global heat transfer coefficient, which is in kilowatt per meter square Kelvin. A is in meter square. All the length dimensions are in meter. Okay, now this correlation is valid when the upper gas layer temperature does not exceed 600 or 600 degrees centigrade or 873 Kelvin. So this is the QH correlation. So again this factor A naught into root of H naught comes into play, the overall internal area and this global. So how to get the global heat transfer coefficient? Research is still going on. Some estimates can be used for getting this. So now as I told you, determining the value of HK is the challenge in using the MQH correlation. It depends on the duration of the fire, thermal characteristics of the compartment boundary or the walls or ceiling, etc. So let us consider the figure below. So any heat transfer problem can be solved by using electrical analogy, electrical circuit analogy. So let us say that this T is the compartment temperature within the compartment, and there is a vent in the compartment of area A naught and height H naught. So you know that when there is a fire, there will be some mass which is coming in to the bottom of the vent opening, and mass which will be going out, hot gases will be going out. So now the resistances for the heat transfer outside the compartment is, see this is wall temperature TW, this is say ambient temperature T naught. Convective heat transfer occurs, the overall global heat transfer coefficient Hk. So resistance to the convection is 1 by Hk into A. A is the area, this area perpendicular to the heat flow. Now within the compartment there is heat transfer due to convection and heat transfer due to radiation, but the radiation heat transfer can be considered as equivalent convective heat transfer with the heat transfer coefficient of HR. That means here the total heat transfer coefficient will be HR plus HC. Now conduction is also there. That is, if the material thickness is say delta, the thermal capacity or thermal inertia is K rho C, and the heat release from the fire Q dot is M dot F, that is the mass loss rate into heat of combustion. Okay, this is the circuit we have. Okay, so from this, if you measure the temperatures, we can have some estimation of the thing, but anyway it is non-trivial. Now several cases appear here for determining the heat transfer coefficient. First one is if the wall temperature, so wall is of say metal or anything, the wall temperature tends to the gas temperature or the internal temperature of the compartment T, then the heat flux is expressed by solving a transient heat conduction equation as Q dot double dash heat flux, that is kilowatt per meter square, is 1 by root pi. This is a solution available for solving the heat transient heat conduction. It is actually in one dimensional, you can say, one dimensional transient heat conduction equation, root of K rho C by time into T minus TA. This is the heat flux. Now wall temperature approaches T. Now the characteristic burn time is less than Tp. Okay, that is del square by 4 into alpha. Characteristic burn time. The Tp is the thermal penetration time. Okay, that for the conduction to occur within the solid, the thermal penetration time, the burn time is less than thermal penetration time, and alpha is the thermal diffusivity K by rho C. Here del square is the thickness of the material divided by 4 alpha will give you the thermal penetration time, the scale of that. So this is lesser than, that is, this is greater than T. Now Hk, in this case Hk can be written as, we are trying to estimate Hk, correct, can be written as under root K rho C by pi T, or we can say K rho C by T. So this is one. Then second one is if T is greater than Tp, that is stationary or steady conduction through wall occurs, then the heat flux can be expressed as K into dt by dx, which is equal to K into T minus TA divided by delta. That's what. In this case, heat flux will be Hk into delta T, correct. So I can say Hk will be equal to K by del. So that means for different materials where the conduction resistance is very low or conduction resistance is not very low, etc., we can use some weighted area approaches, okay, to get the value of Hk. Then now flashover. Basically the MQH relationship is used to find delta T by TA, correct. Now MQH relation can be used to predict the flashover condition. Now temperature rise of about 500 degrees in the upper layer of the gas can be taken as one of the thumb rules. We have seen several thumb rules, correct. So if the temperature rise of 500 degrees, temperature is delta T. So that is the upper layer temperature exceeds 500 degrees, then that can be taken as a conservative criterion for the onset of flashover. So we can what we can do is, we will go back to this equation. In this equation I have Q dot C in the right hand side. Now try to estimate Q dot C using this. Now I know delta T value, correct? So I will try to estimate Q dot C using the other parameters. Take Q dot C to the left side and write this. I get an expression like this. Now substitute the values of known parameters. Okay. Obviously G, rho A, TA, Cp, etc. are known, and delta T also I have taken as 500 Kelvin. Correct. Now I will get QC, because since delta T of 500 degrees will cause flashover, I can say the convective heat flux estimated by using a value of delta T equal to 500 Kelvin will give the heat flux required for flashover, which is calculated as 620 times Hk At A0 into root H0 overall to the power of 0.5. Now here the Q dot FO is in kilowatts, is the rate of heat release needed to produce flashover. Okay. If the Q dot is less than this, flashover will not occur. That is the thing. So by using MQH correlation and by setting the delta T value of about 500 Kelvin, which is one of the thumb rules for the onset of flashover, we have estimated the value of the convective heat transfer rate, which will cause the flashover. Here Hk is in, so Hk can be estimated by one of the ways which we have described in the earlier slide, like this, and this is in kilowatt per meter square Kelvin, A in meter square, H0 is in meter. So this is one of the usefulness of the MQH correlation. Now fire severity. Again, please see that we will go back to the equation D here, which is an expression for a typical delta T by TA, where please understand that the delta T has not exceeded a temperature of 600 degrees centigrade. So now is 6.85 times Q dot C square divided by Hk At A0 under root H0 whole power 1 by 3. So now considering this, recalling equation D, here we have used an empirical constant of 6.85 to determine the ratio of delta T by TA, and this value, the empirical constant, has been determined from experiments where the fire sources are generally located at the center of the enclosure. So if there is an enclosure, the fire source is in the center of the enclosure, but fire source can be anywhere in the corner or towards one side wall, etc. In that case, the equation can be written in general by using some constant Ct instead of 6.85, a number. Now for corner fire, the Ct value will be 12.4 instead of 6.85, and it is 16.5 for the room linings, and so on. You understand? So again, a set of experiments with fire source kept at a corner or side walls, etc. are required to determine this correlation constants. Now please understand that already Hk can be determined either as K by del or K rho C by T based upon whether the thermal penetration time is greater than T or less than T, and this factor A0 is the total vent area, opening area, into root of H0. This is called ventilation factor. This is very important factor for us, ventilation factor. Now the fire severity can be, so you can see that when you have a corner fire or a room lining fire, etc., you can see that the fire becomes, the delta T rise becomes more and more severe because of the increase in the constant values.